So today's talk is about how at CodeLounge we built a data engineering pipeline using CI/CD technologies. This is not a common usage of these kind of technologies, and this is the reason why I thought you could be interested in hearing about our experience. We created this pipeline in the context of a project we are working on in collaboration with the Faculty of Economics, which is on firms and tax competition in the digital economy. For this project, we are collecting, processing, and analyzing data from the Registry of Commerce. So the main data source is the body of entries extracted from the Registry of Commerce. These are basically 4 million text snippets where you can find information about the creation, the deletion of a company, and also about any changes that happen during the lifetime of the company. Maybe the relocation to a new address, or if they got a new director, if they change business purpose, and similar information. We combined this data with many additional data sources, and in order to extract and aggregate all this data, we wrote more than 30 processing components. These are Scala projects. We have a project in Kotlin, some Python components, and a lot of SQL. Here we use SQL to process the data, not to just for querying the existing data in the database as usually. The final result is a relational database with more than 60 tables and 120 million rows. So the problem with this is that if you consider that to recreate this database from scratch, we had to run each of these components one by one manually in a specific order to satisfy the dependencies, and that each of these components access the database directly, then you can realize that this scenario has some shortcomings from an engineering point of view. Some of these shortcomings that we identified are, first of all, this manual process is also a very error-prone process. Then we had code duplication. We had many duplicated data sources. These basically are copies of the same files in the different project repositories. We had limited reproducibility. This is because we were not able to recreate the database in the state which we had it at a specific date, because we didn't have a log of what project versions we used to create database. This is a limitation, for example, if you want to reproduce a study that was carried out in the past. Another limitation we had is that we had a single database instance, and to be honest, it would have been quite hard to create a second instance. This is because in order to do that, we would have to change and update all the underlying processing components to configure them to run on a different database. If you're wondering why one would want to have two copies of the same database, imagine, for example, staging and production environments. And finally, we were lacking validation. Of course, we had unit tests for the individual projects. Of course, we did our best to make sure our queries were performing what they were meant to. But as you know, best effort is not always synonym of a good result. So at a certain point, we realized there was something like some inconsistencies in the data. So we put in discussion all our infrastructure, and we decided to evolve it to something better done. So how we approach this transformation is the topic of the talk. The first step was to create Docker images for each of the processing components. And then we created a new project to orchestrate the execution of these containers. This basically is the pipeline project. This is the final result. This is our pipeline. As you can see, we have it is composed by 5 stages: setup, ingestion, processing, validation, and finalization. In these stages are always executed in sequentially, while the jobs in the stages are usually executed in parallel unless you define dependencies between them. And this is basically what we reused from GitLab CI/CD for this pipeline. We had the parallelism, like the orchestration of the parallelism and the sequentiality of these jobs provided by GitLab CI/CD. So as I mentioned at the beginning, this is not really a common pipeline. In fact, if we compare it to a more common one, the one above may be like the blueprint for the pipeline of one of our underlying projects. And usually you have like a Q&A stage, then you run your tests, you build the image, and if everything went well, you release it. And this basically pushes the Docker image you just created to your image registry. And from there, you can download it or use it to deploy it somewhere. We never deploy our projects. Instead, what we do, we use these images to run our jobs in the pipeline. Let's now see how we solved some of the issues, or all the issues I mentioned earlier. First of all was duplicated data sources. Now we removed all these files from the repositories, and we moved them in a single folder which is located in the same virtual machine where we run the Docker, where the Docker runners run our jobs. This way, we can mount this folder as external volume to our containers that can access the data directly. Another issue we had was traceability and reproducibility. This is solved now because everything that is not versioned in one of the project repositories is now versioned in the pipeline project. The most important thing here is the version of the version of the projects we want to use. So basically the name of the image we want to use to run each specific job. Then I mentioned having multiple environments. This you can achieve using workflow rules. So what we do here basically is that at the beginning of the pipeline, we define some environment variables. One of these is the name of the Docker container that contains our database. So we have 2 containers, one for staging and one for production. So at the very beginning, depending on the environment we are operating in, if you are on dev, we assign a value which is staging DB to the name of the container we want the pipeline to run on. If instead we are in the production environment, we assign the name, like this variable, the name production DB. This way, it's very easy to switch or to run the pipeline on different environments. With respect to validation, well, the whole point of this pipeline is to extract data from the entries of the Registry of Commerce that is not available anywhere else. So where can you get reference data? One way we did this is by using some official statistics that the Confederation provides. But these official statistics usually are at less fine-grained level. So, for example, they provide the number of companies operating in a specific sector at the end of every year. And instead, we extracted this, the same information, but at cantonal or municipality level. And what we do, then we sum up all our numbers and we compare them with the official statistics. This is not perfect, but it's a good benchmark and provides some confidence on what we are doing. Another kind of validation we perform is to compare the values of the last database version with the values of the previous database version. And in this way, basically, we monitor if there is any big change that we did not expect, or maybe if modifying one of the underlying components changed something on an aspect of the data that we didn't expect to be impacted. So we have like more than 4,000 tests that help us monitor all this. Last kind of validation we perform is monitor for inconsistencies. This is better explained with an example. So imagine you are performing some analysis and you realize that, I don't know, out of these 1.2 million companies, there are 6, so very few, that appear to be located in 2 cantons at the same date. And this is something that, of course, cannot happen. So what we do in this case, we create a test where we extract all these companies from the database. And the expected value for this test is the count of rows we expect to find in this table. Doing this allows us to track the improvement or to monitor how these inconsistencies evolve across the different versions of the database. Another important aspect is that of this pipeline is that it allowed us to reduce the downtime and avoid inconsistent states. This too we achieved with a single trick. Basically, what we do at the very beginning of the pipeline, we connect to the Docker container that contains our database, for example, staging.db. And instead of dropping the current database and running all the pipeline on a newly created database, what we do is we just create a temporary database and we perform all the pipeline on this temporary database. And at the very end, if everything went well, this job runs. And what happens here, basically, we rename the staging.db to old staging.db and the temporary database to staging.db. This is basically a hot replacement of our DB. This way, if anything goes bad during the execution of the pipeline, we don't end up having a broken database. And this also allows us to apply this change very quickly, so a matter of seconds, instead of waiting like 9 hours, which is the time this pipeline takes now to run, to have like the updated version of the database. Okay, so before concluding, the whole point of this pipeline was to automatize the creation of the database once you update one of the underlying processing components. So once you have a new release for one of these elements, all you have to do is you open a merge request in the pipeline repository and you update the value of the version of the specific project. Then you commit, and the pipeline starts, and eventually we'll create the new version of the database. So to conclude, we've seen how using this uncommon approach, we managed to go from a very loosely engineered data processing pipeline to a fully automatized one. The issues we managed to solve are: we removed duplication, we allowed reproducibility, we managed to guarantee the correct execution order of the various tasks, we perform a better validation, we nullified deployment downtime, we prevented broken states, and we can easily manage multiple environments. That's it. Thanks for the attention.